Hello friends. So today we are going to discuss the questions from the year 1982, 1983, 1984 and 1985. From 1982 we have one question. For 1983 we are having two questions. 84 once again we have one question, and 85 we are having two questions. So in totality we are going to discuss 6 questions. So the first question, it was asked in the year 1982, and it states that calculate the steady state current in the 2 ohm resistor as shown in the circuit. The internal resistance of the battery is negligible and the capacitance of the condenser C is 0.2 microfarad. So we are given a circuit and we are required to find out the current under steady state condition in this 2 ohm resistance, and along with this resistance we have a capacitor whose capacitance is given as 0.2 microfarad. Okay. And we have to make the calculation at steady state. Okay. And we already know that under steady state condition our capacitor is going to act as an open circuit. So we can say that in steady state condition capacitor, which is denoted as C in this case, is going to act as an open circuit. So we can just modify the given circuit and it will be coming something like this. So this becomes open circuit from here, and this is our 4 ohm resistance and supply is our of 6 volt, and we have a 2.8 volt resistance like this. So this is about 2, 3, 4, 2.8, and this is about 6 volt. So obviously the current through this 4 ohm resistance will be equal to 0. So we can further draw an equivalent of this, and in this case our circuit, the simplified circuit, so this comes as 2, 3 and 2.8, and this is our 6 volt. So this is our simplified circuit at steady state condition because the capacitor is our open circuit. Now we can find out the equivalent resistance. So here this 2 and 3 ohm resistors in parallel, and the solution of that will be coming in series with 2.8 ohm. So you can say 2 and 3 are in parallel. So you can write this as one resistance, and we have this as 2 parallel 3, applied voltage that is 6 volt, and we are having this as a 2.8. Now this 2 parallel 3 and 2.8 are in series, so we can further draw it as with the help of a single resistance. and that signal resistance is suppose our R equivalent, and that will be our 2 parallel 3 plus 2.8, and this is our applied voltage, that is 6 volt. And in this case we can say, let us suppose the current I is flowing through the circuit. So let us find out our R equivalent. So R equivalent is our 2 parallel 3 plus 2.8, and 2 parallel 3 will be our 2 into 3 divided by 2 plus 3 plus 2.8. This comes as 6.6 by 5 plus 2.8, and this will be coming as 1.2 plus 2.8, and that will be approximately equal to 4 ohm. Therefore we can say our R equivalent will be equal to 4 ohm. Therefore we can find out now our current I simply using Ohm's law. So our current I will be equal to applied voltage and our R equivalent. Applied voltage is over 6, R equivalent is over 4. So we get current through the circuit is give 3 by 2 ampere. And this is the total current. And so it will be same current will be flowing through here, and it will be divided in this parallel circuit. We can say this is our R1, and this we can see is our I2 and I1. And we can easily find out, we are only interested in the current through I2, in 2 ohm resistance, that is we are interested in only our I1. Therefore we can say that the current in 2 ohm resistance, which in this case is our I1, and that will be equal to 3 multiplied by total current. So this comes as 3 divided by total resistance, that is 2 plus 3, and multiply by total current I. And this you can say law or rule is also called as a current divider rule. It's called a current divider rule. Okay. And in case we can just, it is quite easy to remember also. Suppose like in this case we are interested in finding out the current I1, and this current divider rule is being used here when 2 and 3 are in parallel. So this current I1 will be equal to total current I multiplied by the resistance through which we are not going to find out the current. That is I1 should I should be multiplied by 3. Okay. Total current I is being multiplied by the resistance through which we are not going to find out the current. Okay, that is our 3 divided by the summation of the resistance, that is 2 plus 3. And similarly, if you want to find out our I2, then I2 is our current through our 3 ohm resistance. Then our I2, we can write it, will be equal to, we can say our I2 will be equal to the resistance through which we are not going to find out the current, that is 2, and divide by 2 plus 3 times our total current I. So this is quite easy to remember. We already know our I, that is our 3 by 2. So we substitute the value, we get our I1 is equal to, this comes as 3 by 5 multiplied by 3 by 2. And this comes as 9 by 10, and which is basically 0.9 amperes. So we have the value of current is 0.9 amperes. Next question, and it states that it was asked in the year 1983, and it states the hollow metal sphere of radius 5 cm is charged such that the potential on its surface is 10 volt. The potential at the center of the sphere is. So we need to find out the potential at the center of the sphere. We are given that we have a hollow metal sphere, so we can just approximate the figure for it. So this is our hollow metal sphere, and radius is given as 5 cm, and potential on the surface is given as 10 volt, and we need to find out the potential at the center, which will be center, let us suppose is O. And we know that the electric potential inside a hollow metal sphere is constant, and which will be equal to the potential at the surface. So this is basically theoretical part. So you can say the potential inside the sphere is equal to potential on its surface. Potential on its surface, and which is basically our 10 volt. So option B is the correct one. Option B is correct. We have next question, and it states that it was asked in the year 1983. States that the figure shows two identical parallel plate capacitors A and B connected to a battery with a switch S closed. The switch is now opened. The free space between the plates of the capacitor is filled with a dielectric of dielectric constant 3. Find the ratio of the total electrostatic energy stored in both the capacitors before and after the introduction of the dielectric. So we have to find out the initial and final energies and the ratio before and after the insertion of the dielectric. So which basically means that initially we are given, so we have two conditions. One is of initial condition, initial condition states that our S is closed. And if you can say our S is closed, therefore we can calculate the initial energy on the capacitors. That is what will be energy at A and what will be energy at B. Okay. And this entire, our capacitor A, capacitor B, as well as the applied voltage V are all in parallel with each other. Okay. So therefore we can say that initial energy stored in each capacitor that is our energy stored in A will be equal to energy stored in B, and this will be equal to our half CV square. Therefore the total energy, total initial energy rather, total initial energy let us call that as our ui will be equal to ua plus ub, or we can say that twice of half cv square. This 2 and 2 cancels out, so we get our u initial will be equal to cv square. This was our initial condition when switch S was closed. Now we come to our final condition when switch S is opened. Final condition S is opened, and when our S is opened, you can see that capacitor A is still connected to the applied voltage, and capacitor B is disconnected from the supply voltage. So when switch S is opened, from here we can say that capacitor A is still connected with voltage V. Okay. And now final condition is S is opened. Along with this, a dielectric is inserted. Dielectric is inserted. So with the insertion of a dielectric, the capacitance of capacitor A will be coming as K multiplied by C, where K is our dielectric constant. Therefore, we can say that capacitance of capacitor A with dielectric inserted if that is given as Ca prime, then this Ca prime will be equal to K multiplied by its capacitance, that is our C. K is the dielectric constant which is given to us as 3. So this becomes Ca prime is equal to 3 times C. Therefore, the final energy stored in capacitor A. Once again, energy stored in capacitor A, let us call this as UA prime, which will be equal to our half Ca prime and our V square, and this will be equal to 3 by 2 Cv square. So this is energy stored in capacitor A. Now capacitor B is disconnected from the supply voltage, that is our V. Capacitor B is not connected to B, but the charge on the capacitor B will remain constant. can say charge on B remains constant, that is our Q will be equal to C times V. And when the dielectric is inserted, the capacitance of B becomes, you can say that capacitance of B, let us call that is CB prime, will be equal to K multiplied by C, and this gives us that CB prime is equal to 3 times C. Therefore, the energy stored in B capacitor B, let us call that a UB prime, will be equal to Q square divided by 2 C prime B, and Q is our C times V whole square, and this comes as 2 multiplied by 3 times C, and we can just sort it out. So we can get our VU prime, that is energy stored in B, will be equal to 1 by 6, and this comes as V square upon this will be C square, V square, C and C cancel out, so this comes as C V square. So it means total final energy. Total final energy, let us call that UF, will be equal to UA prime plus UB prime, and UA prime we found is 3 by 2 CV square, 3 by 2 CV square, and this comes 1 by 6 CV square. So we get that our UF will be equal to CV square, we can take common, 6 will be LCM, so this comes as 339 plus 1, that is 10 by 6 CV square, or we can write UF will be equal to, we can cancel it, this goes by 3 and this goes by 5, so it comes as 5 divided by 3 and CV square. So we found out our initial energy and final energy, that is before the switch is closed and after the switch is opened, and along with the insertion of the dielectric. Therefore, we get ratio is our initial energy, and we have final energy, and initial energy was our CV square, final energy is our 5 by 3 CV square. CV square goes away, and this comes as 3 by 5. So this is the ratio of the energies for the respective initial as well as final. Next question, and it states that it was asked in the year 1984, and it says that two equal negative charges minus Q are fixed at 0 minus A and 0A plus A on y-axis. A positive charge Q is released from rest at a point 2A0 on the y-axis. The charge Q will, okay, so we have to find out what will be the behavior of the charge, specifically whether it is going to go SHM or it will be oscillatory, okay, how it is going to behave. So for we can just draw a simple figure for that. So we have our x-axis and this is our y-axis. We have two charges, minus q, 0 and a. This is also minus q, but 0 and minus a. And we are given that the charge capital Q is kept at a distance of 2a minus 0. So therefore, we can just join them respectively and they will be making same angle. Let us suppose this is our theta, so the other angle will be also called theta. And there will be a force of attraction between, let us call this as A, this as our B, and this point is C. So there will be a force of attraction between minus Q and plus Q, and similarly, or the other minus Q and plus Q. And let us draw that the forces will be something like this. Let us suppose this is force F, and other force will be also over F in this direction. And we can divide this force into two components. Let me draw it separately. So this is our point B and this is our 2a comma 0. And a force F at angle theta, and similarly there will be other force F that will be also angle of theta. So we can divide into two components, and this component will be our F sine of theta, and this component will be our F cos of theta. And for the other force also, we are going to have our F sine of theta, and the second will be also our F cos of theta. And the force, this F sine of theta and F sine of theta are vertical and in opposite direction, so they are going to, you can say, cancel out each other. So resultant force will be only in the x direction, that is summation of F cos theta and F cos theta. So we can say that two forces, this is our charge Q, two forces act on charge Q. First, let us call that as our F1, and let us call this is F1 and this is F2. So this will be F1. Let me name them only F. It will create confusion otherwise. Okay, so we have our F, and that can be resolved in two components. Let me write in other way. So we can say force 1, which will be F, having two components, and these two components will be our F sine theta and F cos of theta. Similarly, force number 2, which will be also equal to F, having two components, F sine of theta and F cos of theta. And F sine of theta and F sine of theta are going to cancel each other. Okay. So we can say F sine of theta cancels each other. Therefore, you can say the resultant force let us call that as Fr will be equal to twice F cos of theta. And we already know our F, so we can say this will be equal to twice multiplied by our F will be equal to K capital Q small q divided by the distance between them. Okay, so this distance is our 2a and this distance is our a. So we can just draw a right angle triangle. Let us call this as O. So this is our O, this will be our B, and this is our C. So this is our 2A and this is our A. So this distance become our 2A whole square plus A square. And for the sake of convenience, let us say this 2A is our equal to X. It will be much more convenient. Let us call this as X. And this will be also coming as X. Okay, where this X is equal to 2A. So the distance comes equal to as distance square. So we get this as X square plus A square, and we have cos of theta. This is our angle theta. So our theta comes as X upon X square plus A square and its square root. Therefore, we can say our force F, resultant force Fr, will be equal to, this comes as 2kq multiplied by q, and we can say this is our X upon X square plus A square, and this comes as 3 by 2. So for SHM, we know that this resultant force should be only proportional to over X. Obviously, there will be negative sign for the opposition in the opposite direction. Okay, so at least we can say from here that our Fr is not proportional to over X. Therefore, not SHM. This we are very sure. But the net force is acting towards the origin. Okay, so we have this resultant force. So this resultant force is acting towards the origin. So as it is going to move the origin, it is going to gain, you can say, accelerate, gain velocity, and at the origin the net force will be equal to 0, but because of momentum it has gained, it is going to overshoot the origin to the other side and move toward the left. And once again, toward the left side, the net force will be once again acting toward the origin. So it will be keep, you can say, oscillating between the negative x-axis and positive x-axis. So it is not SHM, but it is oscillatory. Therefore, we can write that net force acts towards origin O. So therefore, we can say that charge Q accelerates till the origin. Accelerate till the origin, and at the origin net force is 0. Net force is 0, but due to momentum, it will cross the origin and towards the left side. Due to momentum, it will cross the origin and moves towards left, and move towards left. And you can say this process is going to repeat. You can say as it comes on negative x-axis, net force is again towards the origin. Net force is again towards origin. So you can say it repeats. Therefore, we can say that it will be not be SHM, but an oscillatory. So option number D is the correct one. Repeats means oscillatory. So you can say option D is correct. Next question. It was asked in the year 1985, and it states that we have a parallel plate capacitor, parallel plate air capacitor is connected to a battery. The quantities charge, voltage, electric field and energy associated with this capacitor are given by Q0, V0, E0 and U0 respectively. A dielectric slab is now introduced to fill the space between the plates with the battery still in connection. The corresponding quantities are now given as Q, V, E and U are related to the previous ones. So we have to find out the relationship between Q0 Q, V0 V, E0 E and U0 U. So here the important part is that the capacitor is still connected to the battery when a dielectric slab is introduced in the capacitor plates. So you can just draw the approximate figure. So we have two conditions. One is our initial. So under initial condition, we have a capacitor C, and let us suppose it is connected to a battery. V. And in this initial condition, we are given that the charge is our Q naught, voltage is our V naught, and electric field our E naught, and energy is our U naught. And then we have our final condition. Under final condition, we still have our capacitor is still connected with a battery source, that is our V, but now it is filled with a dielectric. And under this condition, we are given charge is now Q, V is the voltage, E is the electric field, and U is the energy. And we need to find out the respective terms relationship. And we know that the battery is connected, so obviously the voltage across the capacitor is going to remain constant because we have not removed the battery source. So this is the first point from here. So we can say that battery is connected voltage across the capacitor remains constant. And let us assume that the dielectric constant of this dielectric is given as K. Therefore, the capacitance is going to increase by a factor of K when the dielectric is introduced. We can say capacitance increases by a factor of K, and the charge on the capacitor, that is of Q, we know is given as C into V. You can say charge on the capacitor that is of Q is equal to C multiplied by V. And finally the energy, sorry, not finally, we need to find our electric field also, and we have this energy stored in capacitor that is our U will be equal to half CV square. And lastly, we need to find out the electric field. Electric field, that is of E, is given as the supply voltage, applied voltage across the capacitor, and divided by D, and where D is the distance between the plates. So this is our D, distance between the plates, which is obviously not changed. So all these are the general description of the formulas, and we are going to modify these respective formulas according to the given condition. So in the first, let us discuss how the voltage is going to change. So first part is our voltage, and the battery remains constant, remains connected, so the voltage remains constant. So we can say battery remains connected, therefore we have voltage remain constant. voltage remains constant, so which basically means that the initial voltage was given as V naught and final voltage our V, and these two will be our equal. So for respectively voltage, this option is our incorrect. Now we come to the capacitance. Capacitance, like we said, is going to increase, that is with C times K multiplied by C naught. And there is no option for capacitance, but we will keep in mind it will be helping us later on also. And next is our, you can say, charge. Charge, we know, we wrote that Q is equal to C multiplied by V, and we substitute value of C, that is K times C naught, and the voltage is same, that is our V is equal to V naught, so we substitute here V naught, and this comes as K, and C naught V naught is nothing but our Q naught. So the charge is going to increase, so we can say Q is greater than our, we can say our charge is going to increase. So let us check the options. Yes, so we are going to get charge is going to increase, and Q is our final, one second, yeah, Q is the final charge. So from here we can say that our charge is greater than our Q naught. Therefore option A is the correct one. Option A is correct. And next is of electric field. Which is our E is equal to V upon D, and both, or we can also write this as V naught upon D, and here both it is constant. Therefore our electric field is equal to E naught, it is not going to change. So electric field option C is also incorrect. And next is our energy. And energy is our U is equal to half CV square, and capacitance we know is our half K times C naught, and voltage is our V naught. They are equal. So we get our U is equal to K times U naught. So it means our U is also greater than our U naught. So energy is also going to increase. And option number D is also correct one. We can say that our D is also correct. Option D is correct. Next question. It was also asked in the year 1995, and it states that two fixed equal positive charges, each of magnitude Q 5 into 10 to the power minus 5 coulomb, are located at A and B, separated by a distance of 6 meters. an equal and opposite charge moves towards them along the line COD, the perpendicular bisector of the line AB. The moving charge, when reaches C at a distance of 4 meters from O, has a kinetic energy of 4 joules. Calculate the distance of the farthest point D, which the negative charge will reach before returning towards C. So we are given the basic figure given to us, plus Q charge at A and B, and this C is having a charge of minus Q, and it is coming from some distance point. And at this particular point, we are given that we are having C is 4 meters. So this distance is given to us as 4 meters, and this entire distance is given to us as 6. So we can say this will be over 3, and other part will be also 3 because it is given as a perpendicular bisector. And we need to find out this farther distance. Let us call this as distance as x. So we can just draw only distance point of view. So we have this over A, B, D and C. So we just call this as our x. So this is 3, this is also 3, and this point is our 4. And let us join this C. So from here we can find out AC. AC will be equal to 3 square plus 4 square, and its square root, we get our AC is equal to our 5. Similarly, we can find out that our BC will be also equal to 5. And at point C, we are given that it is having a kinetic energy of 4 joules. So at point C, it is going to have a summation of, you can say, the potential energy of the charge plus the given kinetic energy. And here we have two charges, charge at A and charge at B. So this potential energy will be nothing but twice of the potential energy of the individual charge, and plus the kinetic energy, which is given to us as 4. Therefore, we can say that potential energy of charge minus Q at C, potential energy of minus Q charge at C, we can call this as our UC, will be equal to, this will be minus twice K, and we have same charge, that is Q and Q, so this comes as Q square, and divided by our AC square. AC we just found out is our 5, and this comes as minus 2, and K is our 1 upon 4 pi epsilon naught, that is 9 into 10 to the power 9. Charges are given as 5 into 10 to the power minus 5. Whole square, and AC is our 5 square. So we can just simplify it, and we know that is 5, they will be square, this square and this square goes away, and this comes as 9 to 18, and we have this as 10 will be equal to 10 to the power minus 10, and we have this as 9, so we can say our UC will be minus 9 of joules. And we know, or we are given rather, that kinetic energy at point C is our 4 joules. Therefore, total energy at C will be equal to our UC plus kinetic energy at C. And UC we found out is our -9. So this comes as -9 plus 4, giving us -5 joules. And it says that calculate the distance of the farthest point D, which the negative charge will reach before returning towards C. So it means at point D, before it is going to return back, for the fraction of second, here the velocity of the charge will be equal to 0. Or we can say for fraction of second, the kinetic energy will be equal to 0 at this point, at D point rather. We can say that kinetic energy at point D will be equal to 0. Okay. And the potential energy at, so let us call this distance ever r. Therefore we can say that, and this will be also our r. Therefore we can say the potential energy at D, that is our UD, will be equal to our minus, and that will be equal because two charges at A and B. So once again this will be twice multiplied by K, and this is our Q square, and divided by our R. Now we can use the conservation of energy. It means that the total energy at C will be equal to total energy at D. You can say that conservation of energy, we have total energy at C will be equal to total energy at D. Total energy at C we just found out is our -9, sorry, -5. So we substitute it, we get this as -5 will be equal to, this comes as 0 plus UD. So this comes as -2. K we know is 9 into 10 to the power 9, and charge is given to us as 5 into 10 to the power -10 whole square divided by R. And from here we can easily find out value of R. So this minus and minus goes away. So we get our R will be equal to, this comes as 2 into 9 into 10 to the power 9 multiplied by, this will be our 25 into 10 to the power -20, and divided by 5. And we can just sort it out, and this goes by 5, and 1 second, oh sorry, here it is 5, not 10. So this comes as -10. So we get our R will be equal to 9 meters, and we got our R is equal to 9 meter. So we can just draw the figure now. This is our D and this is our O. This point is B. So we found out this is our 9 and this we already know are 3, and this we assumed as X, and we need to find out our X. So we can say our X will be equal to, we have this 9 square minus 3 square, square root 981 minus 9, and that comes as 6 square root of 2, approximately 8.49 meters. So this is the value of X, that the distance of point D. So these were the questions which were asked in the year 1982, 1983, 84 and 85. So these were the total 6 questions which we did today. So this completes all the 6 questions. Thank you.